Hello students, today I am going to discuss about subspace problems. In previous classes we have discussed two more problems of subspaces. So let us see the problem. H is a set of all vectors of the form minus 2t, 5t, 3t for any t is a real number. Then find a vector in R3 such that H equal to span V. Then show that H is a subspace of R3. So here what is our vector space? R3 is here vector space, and you can find H is a subset of R3, and you can find a vector which is a span of V. Means here V means vector space. What is our vector space? R3 is our vector space. So here just you have to find one vector from R3 which is spanned by, so that is nothing but H equal span V, and we can show that H is a subspace of R3. Okay, so H equal to vector minus 2t, 5t, 3t, and t belongs to R. So this is a subset of R3. Why? Because every vector in H contains 3 entries. Therefore this is a subset of R3. Okay, so now we have to find a vector in R3 such that H equal to span V. So what it means? H equal to span V means every vector in H is spanned by one vector in V. V is nothing but here our vector space R3. Okay, H equal to span V. It means every vector in H is spanned by one of the vector in V. Okay. So take the vector in H as minus 2t, 5t, 3t for any t real numbers. T is any real number. Suppose if you change the t value, then the vectors also changes. For example, t equal 1, then you get minus 2, 5, 3. For example, if you take t equal 2, then minus 4, 10, 6, like that. So many vectors are there in H. So let us take minus 2t, 5t, 3t is one vector, and this can be written as t of minus 2, 5, 3, where t is any real number. Okay, so therefore minus 2t, 5t, 3t is equal to t into v bar, where v bar is one vector as minus 2, 5, 3. If you multiply this, minus 2 into t, minus 2t, 5 into t, 5t, 3 into t, 3t. Okay, again it gives the same value. So t is any real value and v bar is a vector which belongs to R3. So how can you write here? This is scalar and v bar is vector. So this is nothing but our linear combination of the vector. Suppose minus 2t, 5t, 3t can be written as linear combination of the vector v bar, where v bar equal minus 2, 5, 3 is a vector in R3. So whenever you write the linear combination of the vectors, that is nothing but our span of the vector. Okay, so therefore minus 2t, 5t, 3t can be written as some scalar into vector. Therefore every vector in H is spanned by vector in V, where V is here minus 2, 5, 3. This vector belongs to R3. So by previous theorem, by yesterday's class, what is our yesterday's class? So V1, V2, Vn are vectors in vector space Rn. Then span of V1, V2, Vn are also subspace of vector space. Okay, so here span of linear combination of the vector V means nothing but span of the vector. So already according to your previous class, span set theorem, by span set theorem, span of the vectors is also subspace of vector space. Okay, so here every vector in H is spanned by some vector. Every vector in H is spanned by some vector. So nothing but the span set is also subspace. Therefore you can conclude that H is a subspace of R3. H is a subspace of R3. Every vector in H is spanned by some vector V in R3. So by according to your previous class theorem, span set theorem, span set is also subspace of vector space V. Therefore here we can conclude that H is a subspace of R3. Okay, coming to next problem. If W be the set of all vectors of the form 2a plus 3b minus 1, 2a minus 5b with real scalars, then verify W is a subspace of R3 or not. Here W equal to 2a plus 3b minus 1, 2a minus 5b, where a comma b are real scalars. So while you changing the values of a, b, then the vectors also changes. So this every vector in W has 3 entries, therefore it is a subset of R3. Now you have to verify whether W is a subspace of R3 or not. So that means it satisfies the 3 conditions. 0 bar belongs to W. Second, u bar plus v bar belongs to W. Third, scalar multiplication property Cu bar belongs to W for any scalar, real scalar C belongs to R. If any of the condition fails, then W is not a subspace of R3. Suppose here the vector W, every vector in W is in the form of 2a plus 3b minus 1, 2a minus 5b. Okay. Suppose I will verify the first condition, 0 bar belongs to W or not. So every vector in W is in the form of 2a plus 3b minus 1, 2a minus 5b, where a comma b are real scalars. Suppose I will put a equals 0, b equals 0 in above set W. Okay, then what do you get here? 2a plus 3b minus 1, 2a minus 5b can be written as, so a value 0, b value 0, 0 plus 0 means 0. Okay, next minus 1, 2a minus 5b, a value 0, b value 0, that is 0. So which is not equal to 0, 0, 0, that is nothing but 0 bar. So this value 0 minus 1, 0 is not equal to 0 bar. Therefore 0 bar does not belongs to W. Okay. So therefore first property fails here. Therefore you can conclude that W is not a subspace of R3. So see one more time here. W is the set of all vectors in the form 2a plus 3b minus 1, 2a minus 5b with real scalars, where a comma b are real scalars. Now we have to verify whether the set W is a subspace of R3 or not. Okay. So every vector in W is in the form of 2a plus 3b minus 1, 2a minus 5b, where a comma b are real scalars. This is a subset of R3. So R3 is here vector space. Now we need to show W is a subspace of R3. That is nothing but we have to verify the 3 conditions. 0 bar belongs to W, u bar plus v bar belongs to W, and Cu bar belongs to W for any scalar C. Okay. So first we have to verify the first condition. So 2a plus 3b minus 1, 2a minus 5b. All vectors in W is in the form of 2a plus 3b minus 1, 2a minus 5b, where a comma b are real numbers. Okay. So suppose if you put a equals 0, b equals 0, then what it becomes? 2a plus 3b minus 1, 2a minus 5b equal to. So a value 0, b value 0. Write in this. So 0 minus 1, 0. Then which is not equal to our 0 vector, 0, 0, 0. So that is nothing but our 0 vector. Therefore 0 minus 1, 0 is not equal to 0 bar. Therefore 0 bar vector does not belongs to W. So first condition fails here. Therefore by this condition we can conclude that W is not a subspace of R3. Thank you. Keep watching our YouTube channel.